Thank you very much. In the history of seismology, once in a while, we had really very exciting events. And one of those events was the 1960 Chilean earthquake. And I came to seismology a little bit too late to really experience that excitement. But since that time, I have been interested in this big earthquake in 1960, which excited the free oscillation of the Earth. And you might wonder why I started out with the Chilean earthquake, which is generally believed to be a thrust mechanism. But I'm going to talk about strike slip event. So you might wonder what the relation is. And it turned out there could be a very important relationship, and we are not 100% sure. Well, first, there are two mysteries, and one is 1960 Chilean earthquake, I mentioned. And actually, this work was written in a paper, love waves and toroidal modes observed at Isabela for the 1960 Chilean earthquake. And we worked on this since 2008 or so. And then preprint, the paper was written, and I wrote it and I put it on my desk since 2010. I haven't even submitted it yet. The reason is, still I wasn't really quite sure exactly whether the conclusion was right or not, because the conclusion was so different from the previous conclusion, which looked rather unthinkable. So I wasn't really completely confident about it, so I didn't even send it. And then, as I mentioned, later on this year, there was a big strike slip event in the Indian Ocean that affected my thinking too. Well, let's start with this 1960 Chilean earthquake. And this is really very historically important. And there was a strain seismometer. Strain in this particular case is the extension, change in the length. This instrument was installed in Isabela in California, very close to Caltech. And this instrument recorded a 1960 earthquake, just like this one. And this is really a very unusual record. And this is probably one of the most important historical records in seismology, because the first observation of the Earth's free oscillations, in particular, both spheroidal and toroidal modes, was made from this record. And this is a very famous paper by Benioff, Press, and Smith. And they basically took this record and applied the Fourier transform to determine the spectral peaks. And probably you know there are two modes of oscillations. One is the spheroidal mode, which involves volume change, expansion and contraction. And the other mode is the torsional mode, which is primarily shear motion. So this instrument recorded both of them. And spheroidal mode, in terms of propagating wave, is more closely related to radio wave. And toroidal mode is more closely related to love wave because it's a shear motion. And you can see here, you can see very strong radio wave, R2G2, and R4G4 here, both very distinct waves, radio and love wave, radio and love wave. And odd number waves are missing here. And this is because the fault length was very long, nearly 1,000 kilometers. So there was a strong directivity, and these waves were not excited. The key point here is, just remember only one thing. You can see radio and love waves with about equal amplitude. And for that reason, by analyzing a single record, these people could determine the periods of both torsional and spheroidal mode. There was a gravity meter at UCLA, but the gravity meter records only vertical motion. Gravity meter can tell you the spheroidal mode, not toroidal. So in this sense, this record was very helpful because with a single record, they got everything. So in that sense, this is really historically important record. And that's it. So this has been sitting in Seismolab for many, many years. And this was digitized, but digital records were missing for a long time. But very recently, we found it out. So that's one of the reasons why I decided to look into more detail. And so most important aspect I have to repeat, the G wave or love waves and the toroidal modes are recorded very strongly on this record. And they were very happy to see that and analyzed and got good results. However, there is a very strange situation. When we started looking at recently, it turned out to be very strange. The reason is this. Professor Benioff is probably the first person who built seismometer without any pendulum. Almost all seismic instruments are using pendulum as reference, but in this case, there is no pendulum. It's strainmeter. So this is a quartz rod, nearly 30 meters long, and one end is fixed to the ground, and the other end is open, and you measure the change in this gap as seismic waves pass by. So you can measure the change in the length in this direction. That's the only thing you can measure. This cannot measure the motion perpendicular to the paper because there is no change in the gap. So this instrument basically measures extension in this direction. So what this can measure depends upon the orientation of this rod. If the orientation is north-south, it can measure the extension in north-south direction. If this is oriented east, it can measure the extension in east-west direction. It so happened that they used this big tunnel in Isabella, which is oriented north 32 degree west. So this was in the direction of north 32 degree west. And Professor Benioff, I mean, he was really amazing person. He invented all of these and installed it, and this instrument recorded many, many great earthquakes, and he was very happy looking at his own records. And he extracted really lots of new information. Some of them turned out to be wrong, but that's okay. This is the first discovery, and very often the first discovery can be wrong, and later people can fix it. Anyway, then there were two events. 2010, there was Maori Chilean earthquake here, and this is 1960, and the Maori. So now we had two Chilean earthquakes. So we can now learn something from these two earthquakes. That's a tale of two giants here. All right, and 2010, we had all good instruments all over the world. So no problem. Everything could be determined very accurately, not necessarily 20 minutes, but in a matter of a few days. And it's clearly a thrust mechanism like this one. So plate motion, Nazca plate is moving this way, so this motion is very consistent, and the fault length is much smaller, shorter than 1960. 1960, you see beach ball here. I think I determined this many years ago. It wasn't quite clear how this was determined, to be honest, because in 1960, there were not that many records. So when we had a very small number of records, in interpreting data, you have to make some subjective judgment. So even if we thought this was right, and maybe it's right, this was determined by waves having period of about 200 seconds. And 200-second wave is relatively short for this kind of giant event. Big waves, you saw in the previous slide, have periods longer than 300 seconds. So 1960 Valdivia, Chile event is believed to be largest in history with 9.5. And this 9.5, we sort of estimated from old records. And when you publish a paper, you have to give some number. And I think I explained all the uncertainties which is associated with this estimate. But once you publish numbers, the number tends to walk by itself. So everyone is using 9.5 and saying this is the biggest event in history. And I began to worry about it because it's not that hard number, to be honest. But anyhow, it's believed to be largest. And also believed to be largest thrust mechanism, something like this one. Also, this is a belief by many people. Well, maybe there is something special. And from that single record, Benioff strainmeter, it certainly does look it's something special. Okay, going back to this record, and I can show you the comparison between 1960 earthquake and 2010 Maui Chile earthquake. I said both are in Chile, and Isabela is near Pasadena, and this station is no longer running. However, you see Scripps, San Diego, they have nice strainmeter at Pinion Flats, which is near San Diego. So on this scale, basically, these are in a very similar geometry from Chile to California. And the orientation of this one is north 38 degree west, as I said, and this one is northwest. So it's very similar. Orientation is similar, and the epicenter and location are similar. So you'd expect that if two events are garden variety thrust events, you'd expect the same recording, right? It's not. Again, going back to say R2, G2, and this one are with about the same amplitude, and the period of this wave is longer than 300 seconds. However, Chile, 2010, R radio wave is large, but you don't see any G wave here. And the same applies to here. R4, very large here, but the G4 is very large over here, but you don't see it. And of course, you can see odd number waves because the fault length is somewhat shorter. But anyhow, the biggest problem here is G wave cannot be recorded in this kind of instrument. The reason is, as I said, this orientation, north 30 degree west, is more or less towards Chile from California. So as I said, if transverse wave, like lab wave or toroidal mode, comes from Chile to Pasadena or Isabela, the motion is transverse to the strain rod. So it can't be recorded. However, it was recorded. And very lucky, because of that, they could recover torsional mode and spherical mode. But it's theoretically impossible. So I asked, unfortunately, Professor Benioff passed away. So I asked Professor Press and Smith to see whether there were any discussion around that time, whether that was possible or not. And of course, around that time, seismologists' interests were mainly in the period, not the mechanism or not the size of earthquakes. So as long as those waves were recorded, everyone was very happy, regardless of how it was recorded. So they apparently didn't pay too much attention to this particular geometry. So in a way, Isabela instrument recorded something that shouldn't be recorded, first of all. But since this recording was so good, they came up with very nice results, important historical results on the periods of the torsional mode. That's basically the mystery I'm going to tell you. Actually, I'm going to ask you whether they have any good explanation for that. So this difference is pretty obvious, right? So I will try to first look at more details and try to at least come up with one answer. How come this happened? Well, first we need to look at the geometry more carefully. So this is the Isabela, and this is the orientation of the Benioff strain rod. I say north 32 degree west. So this angle here between the strain rod and the great circle towards Chile, the difference is only 2.3 degrees. So the wave came almost along the direction of the strain rod. So spheroidal mode or radio waves can be recorded very well because the motion is in the direction of the strain rod. However, transverse wave like this one can't be recorded. That's why it is so strange. And technically, if you have a strain rod, you can compute how sensitive this is to radio and lab wave. So for radio wave, the sensitivity is something like this one. And this is obvious. As the wave comes from here, sensitivity is highest. However, the wave comes from here, there is no sensitivity. And toroidal mode, it's different. As I said, if the wave to a transverse wave comes here, the motion is like this one, so there is no change in direction, in the length in this direction. So sensitivity is there. If you take the ratio of sensitivity to G wave or lab wave to radio wave, SGR, that is equal to sine 2 alpha over cosine square alpha, which is equal to 2 tangent alpha. So if alpha is very small, this is equal to 0. So there is no G wave, only radio wave. So if you have 2.3 degree here, Chile to Isabela, sensitivity ratio is 0.080, not completely zero. That's also important. If it's completely zero, there is no way that we can see toroidal mode, but it's still non-zero. And for Chile to PFO, pinion flat, it's actually much larger, 0.33. So this is also very strange. PFO, if any, the ratio should be larger, so love wave should have been recorded with large amplitude, yet it was small. And Pasadena, Isabella, the ratio is small, so G wave should be smaller, but in fact, it was recorded with much larger amplitude than expected. So the whole thing is really quite mysterious. How can we explain this one? And we really, in the beginning, we didn't know what to do. And I asked Benioff, I couldn't ask Benioff, Press and Smith. And apparently they thought about it to some extent, but they thought it's not that important. As long as waves were recorded, that's wonderful. Well, and then later on, Steve Smith analyzed this record. This is essentially from this instrument. Take Fourier transform to determine the spectrum of spheroidal mode and toroidal mode. And there are two events. In 1960, this big Chilean earthquake, and 1964, big Alaskan earthquake, second biggest earthquake. So the biggest earthquake and second biggest earthquake happened in 4 years apart, 1960 and 1964. And rather surprisingly, Professor Benioff installed this instrument in 1958. And then around 1965 or 66, he retired, and the instrument died. So it's really amazing. That looks as if he knew something, and he put it there, and it recorded two events, and the instrument said, my job is done, and then disappeared. But anyhow, these two giants were recorded very nicely. And to give you some idea, this is the 54 period peak, 0S2, the fundamental mode, and this is about 7.5 minutes, still a very long period. So this is only for a long period. And this peak is 0S2, 0S3, 0S4, 0S5, so it's very distinct. So there is no question about this measurement. And also, toroidal mode, 3, 4, 5, 6, all the peaks are here. From here on, it's very difficult to distinguish toroidal and spheroidal mode because they are very close to each other. But if you look at here, both are clearly recorded. And this is for the Chilean earthquake. On the other hand, if you look at the Alaskan earthquake, if you look at the spectral structure around here and around here, this is incidentally called the spectroscopy of the Earth, to really look at the Earth response in terms of spectrum. You can see very obviously very different spectral structure. Alaskan earthquake is much, much simpler. Peak here, peak here, peak here, nothing. However, Chilean earthquake spectrum is very complex. It's lots of complexity here. The reason is this instrument, for some mysterious reason, recorded both spheroidal and toroidal modes. On the other hand, Alaskan earthquake, geometry is very similar, just on opposite side. It didn't record much of the toroidal, so mostly only spheroidal. So the instrument was functioning properly, right, for the Alaskan earthquake. And also, one more important thing, these are plotted on the same scale, and I drew same scale is individually. So I draw this line at 1. So all the peaks for the Alaskan earthquake are probably below this line, right? On the other hand, for the Chilean earthquake, most peaks are significantly above this line. So this means, as far as recorded motion is concerned, Chilean earthquake is much bigger than Alaskan earthquake. So in that sense, qualitatively, maybe 9.5 as opposed to 9.2, which is for the Alaskan earthquake, seems to be reasonable. Okay, let's look at Alaskan Chile again. Same diagram, strain rod, Chile azimuth is like this one, and Alaska is here. So Alaska has large alpha, the angle between the strain rod and the great circle. So technically speaking, Alaskan earthquake should have better sensitivity to toroidal mode or love wave. Yet even for that, it didn't record transverse wave or toroidal mode very well. So if only Alaskan earthquake happened, probably they wouldn't have had nice period measurements for torsional mode because S signal to noise ratio was very poor for Alaskan earthquake. So if you compute this sensitivity ratio again, for the Chilean earthquake, as I said, it's 0.08, Alaska 0.39, much bigger. So if any, Alaskan earthquake torsional mode should be much better recorded on Isabella strainmeter. But the actual observation was contrary to it. For the Chilean earthquake with so big love wave, torsional mode, but for Alaskan earthquake, nothing. So still mysterious. Okay, how strange it is. I want to show you this ratio. This is again Chilean earthquake Isabella, and these blue ones are for spheroidal mode, and the red one is toroidal, torsional, or love wave you might call. So this difference is quite significant. This is very large, and well, the difference is significant, but still about half here. This is the observed one, and it shouldn't be this big. So if you compute theoretical peak amplitude by using standard thrust model with rake angle of 90 degrees, it would look something like this one. So only spheroidal mode, no toroidal mode. You can have small peak because alpha is not completely zero, right? But anyway, this difference is not, this observed ratio is much too large compared with this one. And lower order, it's also the same thing, but I just omitted in here because lower order toroidal mode has some radial component too. So just to summarize the situation in simple words, it looks like this one. So observation for the 1960 Chilean earthquake, to the first order, G wave to Rayleigh wave amplitude is equal to 1. As you saw, you have G2, R2, G4, R4, about the same amplitude. Yet, the sensitivity factor ratio is 0.08. So for this to happen, at the source, or incoming G wave must be 12 times larger than Rayleigh wave. Then it's okay. If radiation pattern is such that the source excited a much stronger love wave, so the ratio to love to Rayleigh was 12. It's a very unusual mechanism. Then if this wave comes to Isabella, so even if Isabella strainmeter sensitivity is not favorable to love wave, still you'd expect love and Rayleigh wave with the same amplitude. So that's one possibility, if this is the case. But of course, standard thrust mechanism wouldn't do this one. So that's why standard mechanism just simply doesn't work. The same applies to toroidal and spheroidal mode. In a way, G over R and this one are the same thing. So observed ratio, as I showed you, was about 0.57 here. Okay, and then this is at least a factor of 5 too large than we would expect by common sense for thrust mechanism. So this is really the mystery, observed strange behavior. So how can we explain, or maybe we cannot explain? And there are several possibilities, however, and I just listed some of them. The first three, the strain rod was not oriented right. North 32 degree west was given by Benioff in the paper. And the Isabella tunnel is so huge, so it can't be too long. However, it can be misoriented. So that wasn't quite clear. So, but now we have modern technology. This is gyroscopic compass, and we didn't have it, but we got help from IRIS, and they helped us to remeasure the orientation of the strain rod. And it turned out it was wrong, not much. So by correcting for that, that angle 2.3 degree actually was 4.5 degree, so which is more favorable for toroidal. So the discrepancy was reduced to some extent. So instead of factor of 12, this incoming G to incoming Rayleigh wave ratio should be 6. But still, this is very large. If you have any thrust mechanism, those of you who computed the radiation pattern for a thrust mechanism, it's very difficult to have this kind of big ratio in the radiation pattern in any azimuth. Okay, secondly, the strain meter is a very difficult thing. It's a strain rod, and theoretically, I said, it should measure extension. However, it's sitting on the free surface, and also it's put in the tunnel. So tunnel has some effects, messing up strain field. So one possibility is strain wave came from Chile, but because of tunnel and some mountains and lakes there, the strain field could have been messed up, so that actually it's not quite longitudinal. That's possible. However, in order to explain that, you really have to rotate nearly 45 degrees strain field, and that's actually impossible. At least we thought it's impossible. Still, there are some die-hard people who said this distortion of strain field near the instrument could have done it. Well, maybe. But to test that, we actually looked at other events. The strain meter is there. So if a similar anomaly happened to other events, maybe that is the case. However, it didn't. I will show you. But the Isabella strain meter functioned perfectly for the 1964 Alaskan earthquake. This is after the Chilean earthquake. And also, this functioned perfectly for 1957 Mongolian earthquake. This is before the Chilean earthquake. So for one event before Chilean earthquake, the strain response was perfect. And another event after the Chilean earthquake, the strain instrument functioned perfectly. It's still possible that in 1960, only for the Chilean earthquake, for some strange reason, strain field was messed up. That's possible, but very unlikely. Okay. And the third possibility, which I want to sort of discuss, well, the traditional mechanism is wrong. We said it's a thrust mechanism, but it's not really a thrust mechanism. So, of course, then interpretation is not unique. The simplest way is to increase a strike slip component. So from pure thrust, we want to go to oblique slip with fairly substantial strike slip component. The question is how much. If 10 degree or 20 degree difference, it may not be that strange. However, you really need to add about the same amount of strike slip component. So if you use this one, the conclusion is Chilean earthquake is essentially 50-50. 50 thrust, 50 strike slip, which is very different from the standard concept of Nazca plate subducting underneath South America. Or another way is maybe thrust event, the Chilean earthquake, triggered another big strike slip event nearby. And we cannot distinguish those two with a single long period instrument. So, in any case, the mechanism has to be oblique to explain this amplitude ratio. And if you do that, we'll see whether data from other stations are consistent or not. And unfortunately, this problem became so obvious because of this particular geometry of Isabella to the incoming wave. And also, quality of Isabella strain meter was much, much better than anything else. So even if we had other data, they are not as good as Isabella. But anyhow, we compared that at the near strain meter and Pasadena long period. I will show you here. And also, this is not inconsistent with Ogdensburg and the Trieste strain record. But let's go to Alaskan earthquake. For the same strain meter, as I showed you, Alaskan earthquake didn't record any torsional mode. So only these spheroidal peaks are very distinct. So for that reason, as I said, the spectral structure for the Alaskan earthquake was much cleaner and simpler. You can see small, almost nothing, toroidal mode, with essentially this noise level. So they are buried in the noise. If you compute for the Alaskan earthquake mechanism, spheroidal and toroidal, that's exactly what you get. Of course, in theory, there is no noise, so you can see toroidal peak, but the noise level is around here, you'll get this one. So this simply means for the Alaskan earthquake, Isabella strainmeter performed as it's expected theoretically. So this tunnel effect or free surface effect or regional effect, mountain effect didn't seem to exist. And also, by the time of 1964, Professor Benioff put another strain rod perpendicular to it. And this one is only for Alaskan earthquake, because for the Chilean earthquake, we didn't have it. And for that component, also theory and observed are very consistent for Alaskan earthquake, spheroidal, toroidal here. Of course, at long period, noise level is very high. But if you look at the range over which SN is very large, this relationship is what you'd expect theoretically. And time domain, it's also consistent. This is a time domain signal, R2G to R3, and this is computed for Alaskan mechanism, and pretty much consistent. And this is another component, G wave, G2, and so on. So for the Alaskan earthquake, we didn't see real discrepancy. Then for Mongolian earthquake, 1957, before the Chilean earthquake, the same thing. The recording wasn't very good like this one, so it's very difficult to see the detail. But Benioff also showed some blow-up of integrated record, and this is observed record, this is computed. And if you look at the very long period end, 300 seconds or longer, they are pretty much consistent, G1 and R1 ratio. So we didn't see that kind of anomaly for either Alaskan earthquake or the Mongolian earthquake. So the conclusion is only for the Chilean earthquake, there is something strange. So how much strike slip component do we need to add to explain the data? So one simplest way is to compare the spectrum. The top one is the observed spectrum, 2, 3, 4, 5, spheroidal and toroidal. And as I said, over here, toroidal mode is about 57% of spheroidal mode. So this is the observed spectrum. Okay. So if you use a traditional thrust mechanism, as I said, toroidal peaks are especially missing. It's within a noise level. So it's way down here. So there is no way you can explain this observation. So you increase the rake angle slightly. In other words, you increase strike slip component gradually. Well, 110, 130, still not enough. 110 really doesn't make any difference. 130, it gets better, but you have to go to either 130 or 140. So 140 is almost 50-50. It's oblique, but the thrust component, strike slip component are about the same amplitude. So only here you get close to this one. So in that case, the Chilean mechanism, earthquake mechanism, if you are to explain it in single fault, it must have this mechanism, which is very peculiar. Nazca plate is not moving this way, moving more like this one. So this is something strange. Either plate tectonics decides not to follow the rule or something. Or one other possibility is really the thrust mechanism triggered big strike slip. But it has to be really big, almost magnitude 9.2 strike slip. And traditionally, we never saw large strike slip event, and so that's mystery. Okay, and I will just show you a few other observations. This is going back to radio wave and the G wave, all right? So this is observed radio wave and G wave. It's very large. And if you use traditional mechanism, you don't see it. Of course you don't. And then if you make it 140, you begin to explain this long period. Short period may not, but this long period amplitude, they become consistent. So looks like this disparity is only at long period longer than 300 seconds. Around 200 seconds or shorter, the traditional mechanism is okay. So Chile, Nyanya, I mentioned, and Benioff had a similar strainmeter in Nyanya, but of course Nyanya is in Peru. Maintenance and everything was very difficult, So it wasn't nearly as good as Isabella. But yet, if you just take observation is spheroidal, toroidal, or something like this one. If you use 90 degree, again, toroidal becomes very small. It's essentially noise level. So if you increase rake angle to 140, they become about the same ratio, or the details don't match. But this is really noisy record. And also, there is Pasadena instrument. And this is a very unusual pendulum instrument. Ralph Gilman, engineer working for Benioff, developed very long period press viewing type instrument around that time. And they computed the spectral peaks. And these peaks, the red peaks, are all actually love wave or toroidal peak. And rather surprisingly, toroidal peaks are bigger than spheroidal peak. And this is actually very unusual because one of the reasons is toroidal or love waves have usually lower Q. So for that reason, if you observe free oscillation, it has a long path. So love waves tend to be attenuated. So we seldom see peaks, toroidal peaks, bigger than spheroidal peaks. Yet in this case, Pasadena, that happened at long period. So if you take this ratio, observed ratio is something like this one, this red one, very large. But if you use standard 90-degree thrust mechanism, it's way down here, this blue one here. So there is no way you can explain this observed ratio. Only if you increase the rake angle to 140 or even 130 around, then they are more or less consistent. So the details are very difficult to see. However, in general, it's very difficult to explain this Isabella results without putting large amount of strike slip. And also, this is a very elegant study by Stein and Geller, and this is splitting of 0S2 and 0S3. Around that time, this was a big topic. Because of rotation, these peaks split. And their point in that paper is, if they use Chilean earthquake mechanism with 90 degree, they could explain data very well. And this is mechanism dependent. So their conclusion was this thrust mechanism was consistent with the splitting. So if we change the mechanism, we have to check it. Then if I change 90 to 140 degree, it didn't change actually. The splitting pattern is essentially remains the same. So basically, this is compatible with observation. Well, there are several really possibilities. So if you go back to Maori event, 2010, even if it looks like it's very consistent with plate motion, but if you really look at carefully the long period mechanism, there is some discrepancy. The discrepancy is this. This direction is a long-term plate motion between Nazca plate and South American plate going this direction. However, the co-seismic slip direction determined from W phase, long period wave, is in this direction. So there is 10-degree difference. So this means long-term it should go this way, but short-term it went this way. So that means this much of motion wasn't released. So this actually corresponds to magnitude 8.3. So in a way, there was some unreleased right lateral slip corresponding to magnitude 8.3 during Maori. So for single Maori, this much of a strain was left unreleased. So if you have 10 Maori type thing, this can be as big as 9. Well, that's one possibility. However, you have to worry about after slip and aseismic slip in between, interseismic period and so on. So it's not quite clear. Or just you turn around the argument. Maybe this happens at each magnitude 9 or something. However, eventually this builds up. And when this really builds up to strain comparable to 9.5 or something, the whole thing goes, producing big Chilean earthquake. So in this case, overall subduction was okay, but each time there is some leftover. And once every 100 years, along Chile, maybe 100 years or so, big earthquakes happen. But then in 1,000 years, this leftover portion builds up to a large event, And if that's released at the same time, you have 1960 type event. So in this case, 1960 type event is not just a garden variety thrust subduction event. It's a very unusual supercycle event, you might call. Okay. Now, an alternative interpretation is that thrust and strike slip events occur on different faults. It's a triggering, and one triggers the other. And that's very possible, and recently we have seen this very often. And there is, I think some of you are very familiar with this. There's something very interesting in Chile. This is the Chilean zone, and there is a very large, long fault, nearly 1,000 kilometers long, Liquiñe-Ofqui fault. Apparently, this is mapped very well as far as the surface feature is concerned. I haven't really been there, and even if I have been there, I wouldn't have recognized it. But anyway, this is mapped over 1,000 kilometers. However, the offset is very small. And this fault is more or less along the volcanic arc here. So there is some strike slip feature along the volcanic arc, and the thrust zone is here. So one possibility is, this is just a surface manifestation of some deeper process, something like somewhere around here with the strike slip mechanism. So one possibility is this thrust event triggered this large-scale strike slip event, and this doesn't reach the surface, but only a small fraction of it shows up on the surface as this long fault. That's one possibility. So basically, conclusion for this part is 1960 and 2010 events are very different. And the 1960 event, a period shorter than 200 seconds, the standard garden variety thrust mechanism is fine. But at the long period, it must have thrust and strike slip. And the long period slip may be precursory or co-seismic, we don't know. But it could be very long period. And probably, if you include everything, still the Chilean earthquake is 3 to 6 times bigger than Alaskan earthquake. So if this is the case, MW 9.5, and the statement that Chilean earthquake is the biggest event during the last 100 years or so, maybe still valid. Okay, so this is a mystery, and I told you everything, and it's a very simple observation. And if you see some problem with this interpretation, please let me know, because I haven't even submitted the paper because I had some concern about the conclusion. The conclusion seems to be good, but it's just so unthinkable. So if there is more reasonable alternative interpretation, it's very straightforward. You know all the observations. Okay, then I have been really pondering on this one. It's strange, but looks real. Then this event happened, this 2012 Indian Ocean earthquake, 8.6. And now we are completely in a different period of seismology. We have lots of high quality data, good computer, good theory, good modeling technique. So we don't have this kind of ambiguity. Just we can compute, we can interpret, and we get very robust results. So Zachary Duptel, who is now at Caltech, basically applied W-phase method to all of them. And this is basically a summary. As you know, 2004 Sumatran earthquake started here and ruptured 1,000 kilometers this way. And this event happened almost close to the trench of this one. So everyone thought in the beginning this could be a big outerrise event. However, the mechanism was pretty much strike slip like this one. Right lateral on the east-west trend or left lateral on north-south trend. We couldn't tell which one was the rupture plane. And then 2 hours or so later, there was 8.2 aftershock that happened here. And after that, there are some strike slip events and the thrust event. So this is a very complex sequence. But anyway, the biggest event had a magnitude 8.6. And W phase is a long period wave corresponding to this portion. And it's very clean, very noise-free. So by using this part of the wave, you can really determine it very well. So he applied this one, and he added something else I will show you. And first, we sort of went back to a very traditional way of looking at all the data. Again, now we have so many high-quality stations, and we do have a way to simulate include three-dimensional structure. But this one is just simply equalization of radio wave and lab wave at 90-degree distance. Then plot all the traces. These are not synthetic. These are observed records. So at this period, from 100 to 400 seconds, it's just amazingly simple, nothing else. Very clear radio wave, lab wave. So if you take the peak amplitude and plot it as a function of azimuth, you see very clean radiation pattern of strike slip events. But notice that this low amplitude here is much bigger on this side than on this side. It's more distinct lab wave. So there is some directivity towards this direction. And note that this direction is different from the direction of one of the northern planes like this one. So this directivity is not very simple. If directivity is along one of the slip planes, you should expect directivity in that direction. But those two directions don't match. That's one thing to remember. Then if you plot it, amplitude, the same thing. This is a diagram you have seen. Look at only this one. This is an 8.6 event. Then there is some amplitude variation. This is the ratio of observed amplitude to synthetic amplitude. So if it's symmetric, it should be 1. But actually, there is increased amplitude towards west, as I showed. And it's very obvious here. And this is for the foreshock to this event in January. And that small event, it's a bit noisy, but there is no directivity. So it's a clean sort of point source in a way. So, and also he noticed that there is some second event about 40 to 50 seconds apart. So, and there is some systematic azimuthal variation. That means maybe the location is not exactly the same. So he applied this two-point source W phase inversion. In the past, we are always using one source. And even one source, there are approximately 10 parameters, 5 parameters for the mechanism, and 3 parameters for location, and 1 or 2 parameters for timing. So for one event, we need 10 parameters. If you have 2, nearly 20. So it's not a trivial thing. And he applied this neighborhood algorithm. Actually, to be honest, I don't know the real details. But it's essentially a Monte Carlo type approach. And he made some assumption. But then at the end, this double source, one event 8.5 and 8.3 for the second event, this is not aftershock. This happened about 100 seconds after this one. Can explain data better. So interpretation is this main shock consists of 2 discrete events. One is 8.5, the other one is 8.3, which happened about 100 seconds after the first event. And if you do this one, waveforms can be explained very well. I'm showing only 3, and this is for the first single event inversion, and W phase is this portion. And you can, of course, explain it very well, but there is some discrepancy like this one. And the later part is not used for inversion, but still the agreement is pretty good, but still you can see some discrepancy. And if you use double point source inversion, basically, essentially you can explain everything. And of course, you have now 20 parameters, so in principle, you should be able to explain it better, but it's rather good to see that it can explain really nearly perfectly. There is very little unexplained information here, so it's not really reasonable to add another source. And seismologists like to show this kind of diagram. It's just this is all the stations for this two-point source model. The only point is with the 2 sources, we can explain modern high-quality data at long periods extremely well. It doesn't necessarily mean the solution is right, but at least this particular solution is very satisfactory in light of observation. So it is very strange because this event happened right in the outer rise area. So one would expect if we say plate motion tend to produce compression like this one, you should have opposite mechanism, right? If compressive axis is this way, then this pattern should be reversed. Or if this is due to outer-rise type thing, you would expect normal fault. However, you do have the strike slip event with extensional axis in this direction rather than compression. And then we sort of remembered that there was a very famous event in 1987 to 1908 in Gulf of Alaska. And this is Alaskan subduction zone. And this is Alaska on the other side. And this event happened sort of nowhere in the oceanic plate over here. And there are 3 events, all strike slip. And the biggest one is 7.7, 7.8, 7.772. So anyway, all of them strike slip. And if you look at the extensional axis, it's like this one. It's actually normal to Alaskan subduction zone. So geometry-wise, it's very similar. And the interpretation for that, we forgot about the interpretation. Actually, we wrote these papers a long time ago. Interpretation was that because 1964 Alaskan earthquake happened, the plate moved this way. That increased extensional stress over here. That produced the strike slip. Why it didn't happen as normal fault, we don't know. But it depends upon the minimum orientation, the minimum strain axis. But anyhow, so in this sense, this event is very similar to the Indian Ocean event, geometrical relationship between the mechanism and the orientation of the subduction zone, and also the occurrence of big earthquake within whatever 20 years or something. Okay, I want to go one more step because robustness of the solution is up to this. Okay, this is a single mechanism solution, and of course you can't explain the directivity very well. Observed radiation pattern is red, and the computed radiation pattern is pretty much symmetric because this is a single point source. But if you add the second event, it becomes better, both Rayleigh and love wave. However, there is still some discrepancy here. In order to explain this discrepancy, it is possible to include some asymmetric rupture for each one of them. And that rupture direction is actually east-west rather than north-south. And this was a bit peculiar because around the 90 East Ridge, there are lots of transform faults in north-south direction. So by common sense, one would put slip rupture in the north-south direction. It's still possible, actually. However, if we are to explain this in the simplest possible model, we would prefer to have rupture direction this way. Then you can explain almost everything. So at least to this point, we would prefer this mechanism and rupture direction. However, other possibilities, you can say maybe this one had the rupture direction this way, and this one, both events may have had this rupture direction, and you can explain directivity reasonably well. So this is still possible, but in terms of goodness of the fit, the other one is better, but we don't want to say too strongly. But there is one more very important thing. This event, magnitude 8.6, is very large. However, if you look at the time history of, say, moment rate function or W-phase solution, the duration of the source is very, very short for the magnitude. So if the duration of the source is short, to the first order, it means maybe dimension in terms of distance. Rupture length is short, although this depends upon rupture speed too. And one important thing is to what depth it ruptured, the depth extent of rupture. And this is very difficult. And for almost all large strike slip events on the fracture zone, in this case, they rupture only shallow depths, down to maybe 15 kilometers or so. And those are all large strike slip. And the largest strike slip events are essentially magnitude 8 plus minus. We hadn't seen anything like 8.6. So the real question is, what is the depth extent of the rupture? And we can use love wave amplitude and Rayleigh wave amplitude to determine the depth extent, the first centroid depth. And the love wave amplitude excitation doesn't really depend upon depth. So from the surface, all the way down to 50 kilometer is essentially the same amplitude. So in a way, you can use lab wave amplitude as a reference. On the other hand, radio wave amplitude, excitation varies tremendously. As you go deeper, the radio wave gets smaller. So, for example, if you have a depth of 10 kilometer, and if you have observed amplitude, you have predicted amplitude, there is a systematic shift, this red line versus dotted line. So if you increase to 20 kilometer, they go close, and then 30 kilometer, they match very well, and 40, 50, 60, then it goes the other way. So in terms of centroid depth, 30 kilometer seems to be most reasonable, which is very deep. 30 kilometer is a centroid depth. And of course, centroid depth can be interpreted in many different ways. Centroid means if we assume a point, this depth is most appropriate. But of course, the source is not a point. So one localized mechanism, if we say source is very localized, maybe it's a very localized source around 30 kilometers. But this is probably very unlikely because this produced local tsunamis, though small. So it's probably ruptured to the surface. So if we say rupture extended to the surface, and if you assume a uniform slip, this goes down to 60 kilometers. However, if you say the slip decreased linearly with depth, then it should go down to 90 kilometers. We don't know exactly, but no matter how you do it, it's most likely that slip extended over pretty much the entire thickness of the oceanic plate. And this is very unusual. Most of the fracture zone, the rupture zone is very shallow. So this seems to be the case in which really oceanic plate can rupture all the way. So in a way, if this is the case, eventually this becomes a plate boundary. So the event was initially interpreted as an intraplate event because there is no known plate boundary. But if actually it broke all the way through, eventually it becomes a plate boundary. So just to give you some relevant number, the numbers at the moment it determined very well, and the central depth 30 kilometers. So if we really want to limit ourselves to very robust conclusion, these are the only conclusion. Of course, we have mechanism. All right. However, if we extend just one step, go one step further by saying that rupture model is right, the total length is only 200 kilometers or so, then you can estimate the amount of slip. So if you use total width of the slip zone, 60 kilometers, then you have a 50-meter displacement. So this means this event ruptured oceanic plate all the way down to 60 kilometers with a large amount of slip, like nearly 50 meters. And if you change the depth, of course, this number will change. But overall, this is about right number, I think. Well, so the conclusion is oceanic plate can break over substantial thickness and distance. That's probably fairly robust for this one. And the mysterious strike slip event during the 1960 Chilean earthquake may be a real event, because that was really the question I had. Because in order to have magnitude 9 to 9.5 strike slip in Chile, we really have to break the oceanic plate over substantial thickness, and which I thought is a bit unlikely, or at least we hadn't seen that. So that's why I didn't even submit the paper. But then after having seen this one, maybe that mystery is not really a mystery, and the oceanic plate can break over large scale. So this sort of is not encouraging. And with the improved data and analysis method, this is pretty important. Seismologists can reveal unthinkable events occurring in the Earth's interior. So in 1960, even if that was real, we really couldn't conclude. I hesitated to publish it because the data were incomplete and you are not completely sure. But now seismology is very different. At least at this long period end, I think our conclusion is very robust. So we really can use seismic waves to understand something very definitively, whatever is happening in the Earth's interior. That's very important in Earth science, because in Earth science, we cannot see directly something in the Earth's interior. But now with better instrumentation, with better analysis methods and everything, seismology can be really used to understand robust what's happening. And however, caveat is, if we really think we have unthinkable events, we need to prepare for unthinkable natural hazards. You may have a big strike slip event, or Mexican fractures, or Mexican subductions. So this is kind of out of questions up until recently. But now I begin to think that, well, this Indian Ocean event was kind of unthinkable event, but now we know what it is. So we have to be rather open-minded in terms of preparing for that. Well, I can conclude it, but I want to give you one thing. This is actually very interesting. Professor Aki, when he gave SSA presidential address, he wrote an article, and he said this: a distinguished mathematician working in the area of geophysical fluid dynamics, I don't know who this person is, once confided to me, to Professor Aki, that seismology is the only decent subject, some of you may object, in geophysics. And these comments bring out the character of seismology very well. Well, what this means, don't be offended. What this means is, in seismology, at least we use the signal coming from the Earth's interior. Now we have tools to interpret it very conclusively, and that's really important. For us scientists to understand what's happening in the Earth's interior, we need to have some very conclusive, definitive evidence. And seismology is now beginning to be able to provide that. That's really wonderful thing about seismology. So for the next generation of seismology, it's all exciting. But he has another sentence here. Or this person said that seismologists are narrow and ignorant. And this means, since it's so interesting, seismology, you can see waves, you can analyze, you can go into endless detail. That's very possible. But by doing that, you don't have time to pay attention to other things. So we tend to be rather narrow and ignorant. We don't know what's going on in other areas. Well, maybe, but not everyone. And however, I am very proud of being narrow and ignorant. And by being so, I think we can really enjoy seismology using sophisticated methods to understand what's happening in the Earth. So basically, mystery is not, hopefully it's not really mystery. That's what's really happening in the Earth's interior. Thank you very much.